Test. I'll start going over it here. Here's the points in the breakdown. You probably remember from either the first day in terms of the syllabus or from the other classes you've had with me, since they're all broken down the same way. There's 3 tests. All the tests add up to 50%, so there's the first idea. 50 divided by 3, 50 divided by 3, 3 tests. Final exam, 25%, labs, 15%, homework, 10%. So if you kind of get out your calculator, you'll get an idea of where you are. Obviously, you can't actually put in any numbers here for test number 3 or the final exam. You haven't taken it. So my general rule of thumb is to do this. You've taken 2 exams now. Take your average of those 2. All right? And some of you did better on this one. Some of you did better on the first one. But either way, average it. And by the way, if you did do better on this one, really good job then, because this was obviously maybe it wasn't obvious, but I think this is harder material, harder test than the first one here. But with that said here, go ahead then and figure out, you know, what are you doing? Eventually, 75% of your grades will be based upon tests. And obviously, you haven't done this 25% and you haven't done that 16%. So good news, bad news here is, well, that's closer to 17. But a 25 and a 15 is 40, so that's about 42% right there. So test 3 and final is 42% of your grade still out there. Of course, we still got a number of labs and homework, so I'd say probably about 50% of your grade is still undecided. Like I said, that's good news or bad news. If you're happy with your grade, maybe it's bad news because you're like, uh-oh, it could go either way. If you're not happy with your grade, that is, I guess, is good news, because that means you've got plenty of points out there to change it here. But again, like I like to do, it's kind of a rough ballpark, is to say, all right, look, I've taken 2 tests. I've got an average. Let's assume that I get that same average on test 3 in the final exam. Where will that put me? So there's an idea. Put that, and make sure, of course, you're doing all the homeworks in the labs, and then you'll find out your percentage. So that's probably the best approach you can do right now. Let's run through these in terms of setting them up. Make sure everybody kind of picks up those loose ends, and I suspect this will probably answer a lot of questions, certainly not all the questions, so feel free to ask some questions either now or in lab or office hours, whichever you feel more comfortable in asking it. I'll start with number 1 here. I started to draw the circuit on the board. This is kind of a simplified circuit of your real one, and so that's kind of step 1. So let me just mention what I did here. Hopefully you'll notice that I already put the 2 resistors together. There was a 1 ohm and a 2 ohm, and those were in series. And so I put them together in this picture, and so that kind of simplifies the circuit a little bit. And so there's my 3 ohm. And also over here, on this part of it, there was a 4 ohm and a 5 ohm resistor in series also. And so putting those together, I have a 9 ohm. So I would suggest that be step number 1. You didn't have to do it that way. Some of you did, some of you didn't. It didn't really matter as long as you stick to the rules of what we called conservation of energy, conservation of charge, Kirchhoff's junction rule and loop rule. All right, but there would be the breakdown of the circuit. Then you got to realize that, hey, none of these are in series or in parallel, so we just have to go back to the Kirchhoff's loops and the junction rule. I'll start with the junction. Here we are. If we look at this junction, the way I've set it up, it looks like current number 1 and current number 2 are flowing into the junction, and then current number 3 comes out of the junction. And so what goes in has to go out. That was our conservation of charge we discussed back in chapter 27. So I would call that equation number 1. Obviously, we're looking for 3 equations because we have the 3 unknowns. What is the current in 1, 2, and 3? So the other 2 are 2 loops. Do a left and do a right, or do a full one. It doesn't matter. Just don't do all 3, because you got to do the junction plus 2 others. And I like to just do the smaller of the loops. And so if I do this loop here, maybe starting down in this corner and going around, I would say there's a positive 6 volts. Then there's a minus 3 I1. Then I'm going against the current. So there would be a positive as I come through here. That would be against the current, a positive. Then I go from the big bar to the little bar. That's a drop in voltage, and that gives me 0. So there would be equation number 2. Equation number 3, again, maybe I'll start down in this corner and go in a clockwise direction, but there is 3 there is minus 3I2, again going with the current, so it's a minus, and the resistance is 9, and it's I3 equals to 0. So if you pick the current in those directions, these are the three equations you have. Obviously, you can have a lot of variations on this depending on whether or not you put the resistors in series together, or depending on whether or not you chose different directions for your currents or other options if you did a mesh current, whatever the case is. But somewhere along the line, hopefully you had three valid equations, because those valid equations reduce then to this, that the current in number 1 is 0.714 amps. The current in number 2, chosen this way, is a negative 288. So what that tells me is the current is not going in the direction that I kind of thought it was. I was kind of guessing. It's hard to tell in that center one. We certainly have a small battery pushing it that way. We have a bigger battery trying to fight it. So it's hard to anticipate which way that one's going to go. And clearly then with the negative sign, it must be going this way. So this battery is charging up, which, by the way, when I was making it was my intent, because it's that 3-volt battery, standard lithium-ion battery. This is your phone's plugged in overnight, right? So we're charging our battery here. And so the current's going through that direction. And then current number 3 comes out to be 0.429. So as we fill in that chart, which then says, give me the current in each resistor, number 1 and number 2 are in series. That's where I got the number 3 here. So they're each a 0.714 for those two. Resistor number 3 is this one here. I didn't modify that in any way, and so that is the current in number 3. And resistor 4 and resistor 5 are these two that I had put together. They were the 4 ohm and the 5 ohm, so they must have the 0.429 and the 0.429. So there is the current in each of the resistors. And then once you get that, you're asked to figure out what the voltage is, and the voltage is just Ohm's law there. Current times resistance, current times resistance, and current times resistance. So if you go 1 times 714, you get 714. If you go 2 times 714, you get 1428. This becomes then an 864 negative, depending on your definition of plus and minus. Wasn't going to pay too much attention to that. 3 times that is 1.716, and 5 times that is 2.145. So there's the voltages. Okay. So again, 3 equations, 3 unknowns. Hopefully, again, you put that matrix into your calculator and did your reduced row echelon form. 2. Now, 2 turned out to be a little tricky for a number of you. Wasn't this a homework problem? Yes? No? Okay, good. I just needed to confirm that, because when I was grading this Sunday, I was like, oh my. I didn't want it, because I know it can get a little tricky, and I think it takes a little too much time if you hadn't seen a little bit of it before. And since it was on the homework, I was feeling better that I go, wait a minute, I know this was on the homework. Anyways, all right, so good. You guys confirmed that. So hopefully you did do the homework, and hopefully you did see it. If not, I guess shame on you, but hopefully you figured it out anyways during the test. Might have taken a little more time if this is the first time you saw it, and you may have paid the price on that in number 5. But here's the circuit. The circuit looks something like this. Here is the 9 volts. Here is the switch. And it's got this bridge here. And a capacitor set in the middle. That's a terrible picture. So is that one. So, all right. But here's our values. We've got 1 ohm here, we've got 5 ohms here, we've got 2 ohms here, we've got 4 ohms here, and 10 microfarads here. And here's the thought process, and here's what would have taken a lot of time perhaps during the test if you hadn't seen this one before here. But the real key here in A is it says the switch has been closed for a very long time. Now that tells me then that the capacitor is going to build up to a certain charge and then nothing else is going to flow through it. And so that circuit then quickly changes to looking like this. And that's a big step right there, is to say, look, there is no current flowing through that capacitor. It has built up to some charge, and that's what this one is after. What is the charge on that capacitor? And so if I call this 9 volts here, and I put these two together, which is 5, and I put these two together, which is 7, I can see the current in this one. I'll call it current number 1. But as I go across here, the current number 1 would be 9 divided by 5. That's 1.8 amps. So this little loop right there gives me 1.8 amps, whereas current number 2 would be 9 divided by 7, which is 1.29 amps. And so we'll call that current number 2. So there's our circuitry, if you will. That's really the same as this problem here. So that really isn't the big test here in this question, since we just did that one. But it was get you to realize then that this capacitor that you put across here is going to have the voltage that's between those 2 points. So we want to find that voltage. And probably the best thing to do is to find the change in voltage right there. That change in voltage is that resistor right here, the 4 ohms. So when you go IR, the I is 1.8 amps, the R is 4, and I wrote that down somewhere. 7.2 volts there. So this point here must be 7.2 volts. Kind of makes sense that it's got to be somewhere between the 9. It's a 9 and then you lose a little voltage and then you lose a little bit more. And this is a 1 compared to a 4. And so obviously it's somewhere between a 0 and a 9. In fact, must be closer to 9 than to 0, since this resistor is higher than that resistor. All right, so that's the voltage at that point. The voltage at this other point would be the same idea. Why don't we calculate the change in voltage? So calculate the change in voltage there. And so again, that would be an IR. And in this case, it is the 2 ohms. So the resistance is a 2. The current is the 1.29. And if I do that, I get the 2.58 volts. And so there's the voltage at this point. So by hooking a capacitor between them, then that must be the change in voltage on the capacitor. One side is at 7.2 volts, the other side is at 2.58, coming to a difference of 4.62 volts. So there's your calculation. And like I said, a lot of thought goes on in here for a short time test. So like I said, hopefully you had some time to think about it before the test. But that was the key step. What is the voltage between them? And so those 2 things. There's number 1, what is the fact that there is no charge flowing through that branch, if you will. And then number 2, I just got to get the voltage on either side. Now once I get that, then it just comes to capacitance is charge divided by the voltage. So we know the capacitor is a 10 microfarad. We just calculated 4.62 volts. We can get the charge by moving that over to there, and we get 46.2 microcoulombs. So there's A. What is the charge on that capacitor? Because then the next thing's going to happen is we are going to open that switch. And again, here's a lot of thought process too. And again, maybe a little too much to ask in a short time scale. But if you open that switch, watch what happens now. You have just said that this side has gotten positive because it's at a higher voltage, 7.2, and this side is now negative. And so when you open that switch, this positive is going to be able to flow to the negative, and this positive is going to flow through to that negative. So we have a discharging capacitor. And that was the key to realize then that I've got a capacitor and it's going to discharge. I've got a 10 microfarad capacitor and it's going to discharge through two resistors, actually, two that are in series. So that takes some thought too. But if you'll notice, it was set up, hopefully the math was pretty quick here. This is a 6 and this is a 6. So we've got two 6s in parallel, which comes out to be a 3. Maybe I'll do the math over here to say, okay, I've got a 6 and a 6, which come out to be a 3. So there's our circuitry in our discharging capacitor. Okay, capacitor, discharging, and it would look like this. This is the equation we worked out for a discharging capacitor. And you can run through the calculus again, as some of you did, and I got no problems with that. Maybe a little concerned that it may eat up a lot of time, a valuable time for later on, but there's the equation for the discharging capacitor. So I know that it starts with the 46.2 microcoulombs over there, and then the time is 30 microseconds, and that's my question. And B, what is the charge on the capacitor 30 microseconds after the switch was open? And the time constant, tau, is RC. So this is the 3 times the 10 micro, which, again, you can see the setup was designed to get that to be e to the negative 1 there. So you've got 30 microseconds divided by 30 microseconds, which is e to the negative 1. And so the final answer comes out to be about 17 microcoulombs. So there's your final answer for number 2. Oh, now number 3 is where we shift gears from our circuits into our magnetism, and got a square here. And actually the first part of it, A, is still with our circuits, but when we get eventually to C, then there's a lot of angles involved and quite a bit of work to do in C. But in A says, all right, you have a voltage and you have a resistance. And in this case, the resistance is created by just the wire itself here. The voltage is a 1.5 volt battery, so the voltage isn't much, but hopefully puts out a lot of current, kind of like this car one you'll see here today. Not much voltage, although that's 12 volt, but it's got a lot of current that it can put out. And in this case, we've got the resistivity, the length, divided by the area. And so that was our fundamental idea of where does resistance come from. The rho is the resistivity of the material, L is the length of the wire, and A is the cross section of that wire. And there's a temperature dependence, but wasn't really needed in this problem here, or at least listed in this problem. So we'll just use the resistivity that's given, which is the resistivity at room temperature, which is kind of the intent here, although there's so much current in here that this wire is probably going to be warming up pretty quickly. But that aside, is the length of the wire is 8 meters. So you take the wire and you make it into a square, 2 on a side, so that's 8 meters. The area then is the size of this wire. It does give its diameter, so don't forget to cut that in half. but that would be the cross-sectional of it. And so there's the 1.5 over the 1.7 times 10 to the minus 8. There is a length. Let me put the number in there as 8. And then I'll move upstairs the pi. And then I think this was 3 millimeters for the diameter. So let me change that to a millimeter and a half and square it. And so if you put all that in there, you get just a hair shy of 78 amps there. And so there's A. How much current is flowing in this little square? And then B is a straight application of what is the magnetic field from a finite size wire. And depending if you want to use cosines or sines is kind of your choice, as we talked about in class, depending on your view of the angle. By far, most people did the cosine, so I go, okay, I'll do the cosine too. And maybe I should just draw a little square here. But again, the B, a lot easier than C here, is saying, all right, what is the magnetic field? Now, this is what we know from one wire. So we need to look at that wire. This would then be 45 degrees, so I'll put in a 45 degrees there. And then if we started on this end and went across, then this angle would be 135. So this is 135. So there's my two angles for getting the magnetic field from one straight wire. Now there's 4 of them, so I guess I got to technically do this 4 times unless I notice something. And that is in every wire the same length, the same distance, the same angle? Is the magnetic field the same direction though? Yeah, fortunately it is. But not in C. But in B, yes. And so if I take the current as given in this direction, this direction, this direction, this direction as it goes around the loop, take my right hand, it would be out of the board from this wire, out of the board, and out of that board. So everyone gives me an out of the board. So how about I just go times 4? And then I can get it for one wire, multiply it by 4, and say it's out of the board here. So putting in my number here, I'll start with these two grouped together. That's 1 times 10 to the minus 7 there. The current I just did, that's the 77.96 amps. A is something to think about here. A, if you remember from the derivation, was how far are you perpendicularly from that wire, which in this case is 1, since we're at the center of a square that measures 2 by 2 by 2 by 2 there. And so I'm 1 meter out. And so then the cosine of 45 is root 2 over 2. And then 35 degrees is the negative of that. So maybe I should just put times 2 and then times 4. But once you punch all those numbers in, you get 4.41 times 10 to the minus 5 Tesla, or micro Tesla. So about 44 microteslas here for the magnetic field from B. And then C, purposely divided the problem into an A, B, and C so that I can kind of get the gist of what you have. But C was the real challenging one. And the one most people miss, as to be expected here. But we're outside the square now. And where are we? And our angles are a bit more complicated here. But we're over here at point Q, 1 meter outside. So that means this across there is 2 meters. And if I separate this into maybe wire number 1, wire number 2, wire number 3, and wire number 4, the magnetic field is going to be a combination of all 4 wires. And fortunately, 2 and 4 are going to be the same, but not cancel out, unfortunately, but at least they're going to be the same. Wire number 1 got a little bit of work to do here. I need to find that angle. But if I go tangents of this angle, I'll call it theta 1 for a moment, that must be the opposite, which is 3 over a 1. And so that comes out to be 71.6 degrees there. Which means then if I did that, that angle there, I guess, is 100 and, well, why don't I just break it into 2 pieces. This angle then, since this still would be a 71.6, if it was 72, I guess that would be an 18. So that must be an 18.4 in there. So this angle here, which I'll call, I guess, cosine 2, must be 90 plus that, which is 108.4. All right, so that helps me out here. What I can do then is write it as mu naught times I over 4 pi. The distance away is 3, and I have cosine of a 71.6 there minus the cosine of 108.4. And so that would be the magnetic field from that first wire, which in my notes I called the left wire. Came out to be 1.64 times 10 to the minus 6 Teslas there. Two, which is the same as 4, is unfortunately not going to cancel. If I grab my right hand here, this is going to be coming out, and then the current goes this way, and that one's going to be coming out. So although they're going to be the same, they don't come out here. So if I go to put in my numbers, it's a mu naught I over 4 pi. And again, remember the A is the perpendicular distance away. So that's a 1 meter there. Cosine of, and maybe I'll just look at wire number 2. The initial angle then is the 18.4. And then minus the cosine of, and fortunately that one's 45 degrees. I won't have to do too much thought there. It's 1 unit up and 1 unit over. So there's a cosine of 45 degrees. And so that one comes out to be, ooh, and I guess I didn't do it separately. The two together is 3.77. So I'm just going to divide by 2 there. What is that? 15. I'll just call it an 8. So is that a 9, roughly? If you wanted to know what it was individually, 1.9 milliteslas. And then number 3 is probably the easiest one at this point because it is the same as what we just did here. So it's got to be 1/4 of this total. And so that would be an 11 microteslas there. Since we basically did 4 of those same wires and did that. Now that's what they are individually. You got to be careful here because we do want a total. And their directions do have a slight variation. The first one is out, second one is out, third one is in, and the fourth one is out. So we would have field 1, field 2, field 4 minus field 3 is probably the best way to write it here. And if you do that, then field number 3 is a little bit stronger, so you do end up with a field going into the board as hopefully expected, because this is current going in a loop. And so we learned that if you put your fingers in the direction of the current in the loop, you get out, and that's for the part that's in the middle of it. And we also learned that there were no monopoles, so if the flux comes out this way, it's going to wrap around, go back in, and circle. So we know that anything outside of the square, it's got to be going into the board. Any place in the square must be coming out. Yeah?
So it's a positive at that point?
Well, negative if you call...
You said into the page then, right?
Into the page, negative, right.
So the true magnetic field is coming out of the page?
No. I'm calling out of the page positive.
Okay.
So my result is into the page. Right, negative. So positives mean out of the page, negatives mean in.
Is that the convention?
Yeah. I mean, in your math class, didn't you do a lot of, I mean, I'm not a big one for conventions, only when they're useful. But I think the convention is this, right? Out of the board, positive, right? So this would be a negative k-hat direction. Yeah. But that's why I guess I always say, go ahead and just, tell me either into the board or out of the board or to the left or to the right or up or down or whatever. Because, if you just give me a sign, then I kind of, just, okay, well, I'll have to judge that on the convention. Yeah. All right, and then number 4 probably made you feel a little bit better after going through number 3 there and all that long, but you guys seem, at least the majority, just seem to nail number 4 here. This is this mass spectrometer that we talked about. We did tie it together, though, with the field from the solenoid. That might have been the hardest part of it, because that was something we did just that last part of the week here. But hopefully in the first part here, you realize that, okay, in this part there is an electric field, and they label the electric field at 100 newtons per coulomb. And at the same time, there is a magnetic field pointing out of the page. And this part of it, if you remember our discussion, was called the velocity selector. And the whole reason there was no bending to what in this case we are sending protons through is because the force electrically, as viewed I guess this way, would be over here to the right, but magnetically then V would be down and B would be out, so there would be a force the other direction for the magnetic field. And in order for then these protons to go straight through without being deflected, that's principle number 1, is that the electrical force, QE, has to equal the magnetic force. And the magnetic force is QV cross B. Set up so that they're at a right angle, then it becomes QVB. Q's cancel off, and the velocity then is E over B. And so there I would say is principle number 1. Can't really do anything with it yet because we don't know the speed of these protons and we don't know the strength of the magnetic field, although we do know the third one, which is the electric field. But then they come to the end of their parallel plate, and the magnetic field continues on. And so they arc in a circle. And so then we just have the magnetic force for the net force. The electrical one goes away. And since it goes in a circle, that must equal to mv squared over r. And if we cancel off a v here, I guess we get qb equals to mv over r. And so there I would say principle number 2 plays a role there. Now there we can finally do something, because now we have our 2 equations and 2 unknowns. Here we don't know v and b, but here we don't know v and b. But we know q, we know m, and we know r. And so maybe putting my v into there, or solving for v, as some of you did, but I chose to substitute out the v by calling it E over B, putting the B's together, and I got the magnetic field squared is the mass times the electric field, the charge, the radius. And so after a little bit of calculator work, we can get the field, which comes out to be 9.32 times 10 to the minus 3 Teslas. And so there's our chapter 29 stuff where we did some mechanics and the force from the magnetic field. But as we tie that together with chapter 30, we learned how the strength of the field is calculated based upon current, and then we learned it depended on what shape you have. And in this case, it's a solenoid. So we have a solenoid, and this was the equation we had for the solenoid. And again, you could work through Ampere's law and derive it, and as some of you did, that's fine. And then we came up with 9.32 times 10 to the minus 3 there. This is our 4 pi times 10 to the minus 7. The n was not given directly, or at least the little n. The big N, the number of turns was, the number of loops, it says in the problem is 75. And the length of the solenoid is 15 centimeters, and so the unknown there becomes I, and so there's the final step coming to be 14.8 amps. So this magnetic field must be created from the solenoid. It didn't ask for the alignment of the solenoid. I know some of you were asking me during the test, so maybe it's worth addressing. But if you're going to get the magnetic field in the direction indicated here, we know that the solenoid makes a field that's along the axis of symmetry. So you can't really draw it in this picture, but the solenoid then must be a coil here, and then maybe the wire goes with a little gap to the other side. And so we've got maybe a magnetic field that looks maybe something like this one here, where we've got a solenoid here, then a little gap where the experiment is, and then a solenoid picks up on the other side there. And so there's how we make the magnetic field. And then what was supposed to be the hard one, probably was the hardest one, is number 5, a little electromechanical device. And I saw this problem and thought it would be a good one, although I was concerned that it was too mechanical, and so I divided it into 3 parts and go, okay, I'm going to do an A and a B so that I can see if they still know their magnetism stuff or learn their magnetism, and then I'll leave the C on there to see if they can tie their magnetism into their mechanics, and didn't want it to be too punishing if you didn't remember your mechanics, but at the same time it's obviously important that you do remember your mechanics. I'll start with A. It is a toroid, and the A says then, what is the magnitude of the magnetic field near the outside wall? So this was just a straight plug and chug type of problem, or you could derive the equation using Ampere's law for what is the magnetic field from a toroid. And so as you can see, there was the magnetic field from the solenoid. And this is the magnetic field from the toroid. Both we derived in class, both we did a lab on it, and both of which we are going to need endlessly in these next 2 chapters we're about to do. So if you didn't commit those formulas to memory, or what the shape and what the strength is from the magnetic field, do it now, because it'll kill you these next 2 chapters and the next test, because we need these magnetic fields. And toroids and solenoids and wires are good ways of getting magnetic fields, as you can see: wires, solenoids, toroids. Okay. All right, but here's the toroid. They do say that the toroid has 9,000 loops wrapped around it. Our mu naught, in fact, I'll just put it together with the 2 pi, so that becomes a 2 times 10 to the minus 7. The current was given as 14 amps in the toroid. And then it says the outside wall. And I hope that was clear. Some of you asked, I didn't really debate on what you meant by outside, but further out, radially outward. So we have a radius of 5 centimeters and a radius of 6 centimeters. So near the outside wall would be the 0.006, but yet inside the toroid. Because what's the magnetic field outside the toroid? 0, right? Outside the solenoid. Yeah, that one, roughly 0 too. That one's less accurate, but nonetheless, that's what we're going to do, particularly as you see us get started in this next chapter. Well, like I said, this was and this is, like I said, when I saw this problem in one of the older editions of the book, I go, this will be a good test problem, but let me break it apart, because I wanted to make sure you could do this much of it for sure. Anyways, but that comes out to be 0.42 Teslas there. So a pretty strong field. Maybe I'll draw a picture here. Here is the toroid. It looks like it is got a set of wires that looks more square in its cross section. You might remember the one I passed out in class 2, actually. One had a circular, one had a rectangular cross section. But this one looks more square. But here's where the application comes in, and here's why A, it's a tough problem, and B, I thought it would be a good one for a number 5 on the test here, is this is an electromechanical device. This is, let's use this magnetism for a purpose, for something useful. And I hadn't really given you many examples of that. Well, we'll see more today here, but I was like, okay, this might be, a good one that's going to make them think through, which is why I had said earlier with that capacitor that hopefully you didn't have to spend too much time thinking about that one the first time, because this one's going to take some thought. But here's this idea that if we pass then a current through here, what will happen? Well, hopefully you put that together with the fact that there would be a magnetic field, and it would be inside the toroid, either wrapping around as viewed from above clockwise, or wrapping around counterclockwise as viewed from the above. But it's somewhere inside of that toroid. But this was the fundamental idea that there would be some kind of lift on here, and that lift would come from the fact that the current is flowing in a magnetic field. So in this small area, there is a magnetic field between here and here. There isn't here, and there isn't here, but current and a magnetic field would get a force. And if you use your right hand, if the current is going this way and the magnetic field is in, you would get an upward push. If the field was out, you would get a downward push. Obviously, the downward push is not what we want if we're trying to lift that little weight hanging off to the side here. So we must want a magnetic field that is into the paper at this point, or viewed from above in a clockwise direction. So in here, out here. So that's B. What direction would the magnetic field need to be in order for this to take place? So again, chapter 30, chapter 29. And now, making it into a electromechanical device, let's actually lift something up. And so there's C. And the first part of this mechanics question is this a translational problem or is this a rotational problem? And it is a rotation, so hopefully you did torques, not force. In fact, the way this is set up, because the weight is further out here, we would want the upward force here to be greater than the 50 grams. Because, you know, of our mechanical advantage we have here, or you might call this a mechanical disadvantage here. All right, but the idea here is torque from gravity added to torque from my magnetic field better be 0, or my torque could be a hair more than that if I'm actually going to lift it up here. But let's just set it equal there in our first step. The torque from the gravity is probably the easiest one here. Just going back to our mechanics, torque is R cross F. In this case, I am looking at a distance as we go out to here of 10 centimeters. Since this is listed as 4, and we've already decided that that was 6, because, well, they said the diameter was 12. So this is a 6 and a 4, so we get a total of 10. So I would put for my R 0.1. My force would be its mass. And I guess we can debate if you want to do it in grams or kilograms. I prefer kilograms because that's what I'm going to do here. I'm going to do newtons over here, so I better do newtons over here also. So there is my mass, and there is my 9.8 meters per second squared. So there's your M, there's your G. I guess you could even say sine of 90 degrees. I didn't make it quite as clear as I could be with the angle, but fortunately that angle would be the same as the other angle, so whatever angle it is, it cancels off when I do the torque on that side. So I don't know, maybe I should just put theta. I don't know. Some people, you know, left it in terms of theta, and that was fine, but then noticed that since the two torques have to add up to be 0, it didn't matter there. I wish I had said, you know, it was level and 90 degrees if that gave any confusion. I didn't get the impression that that was the confusion. This was the confusion. How do you calculate that torque there? But this first one is the easier of the two. This is the 0.049 newtons per meter. And so there's the torque pulling it in what I would call a clockwise direction, which we usually labeled that as a positive torque. So there's my positive torque, yeah.
Did you say newtons per meter?
Oh, I think I did say per. I apologize. No, I don't want to say per. Newton meter. Yeah. Newton meter. Which. Then the more interesting one, in part because I don't think we did anything like this on the homework or the lab, is put together your knowledge of magnetic fields and your mechanics, and you're going to see some R's cancel off, so it actually turns out to be a pretty easy integral. But that's the other part. An integral, sure, because one thing that hopefully you're noticing here is that each little section would have a lift. Each little section would have a lift. Each little section would have a lift. Is each little section going to have the same torque? My guess would be no. It actually turns out to be a yes, but it's not that obvious. All right? But you need to set this up and say, no, it's not. Each section is not going to have the same torque. Why would I say no? Right, and I hear both. There's two reasons. Number one is the magnetic field is not the same as you move across in there, right? And so for that alone, I wouldn't expect to get the same torque. But also my distance is changing. So I don't expect to get the same torque as I move along here. So I might do something like this. I might say a little piece of torque would be its position times a little bit of force. That's probably the place to start here with your calculus and say, all right, if I look at one little section, let me just kind of redraw it right here. That one little section is going to have a little force, dF, and it is going to be pivoting around some distance r. And both R and F are going to change at different locations. As I go further out, I have a different R, and as I go out, I have a different magnetic field. And both of those should change. Turns out they change equally, and so the net effect is no change at all. But like I said, I'm not so sure that is obvious there, but I would write this then as dF as the current times a ds cross a b. And so there is our little bit of force on a wire that we learned back in chapter 29 here. And so if I put that in, I can put the current, I can put the distance dr, I can put the magnetic field, and then fortunately the cross product is 90 degrees regardless of what angle it's at, because the 90 degrees is not the angle here, but it's the angle between the current and the magnetic field. And so the current is going along that metal piece, the catenary, and the magnetic field is going this way, and so they're 90 degrees.
Is it okay to write the V on the right side of the R?
Yeah, there is not a standard convention. What do you mean by the dr here? And I think what you're getting at is when I do an integral, okay?
I'm saying, does that imply V is constant when you do it that way?
No.
Okay, never mind.
Yeah, no. I'm not saying B is a constant. But what I am trying to say is some of you may be familiar with integrals listed in this form. Others of you may be familiar with integrals listed in this form. And I think here at this school we mostly see this. Is that a fair statement? And when you do it this way, it has something negative about it. That is this supposed to be part of the integral? Or is it something outside of the integral? And this notation does say it's part of the integral, so they're trying to say the same thing. But this notation is nice because it quickly tells the reader what are you integrating with respect to. And so I would agree that it's a less common notation, but very useful notation. I do tend to stick to this because this is what I know most of my students are familiar with here. But I like this. I like this a lot. But I'm not going to change the math department, and then I'm just going to confuse you guys. But I learned it this way, and I really like it this way. But both of them have their advantages and disadvantages. Yes?
What context is that second one generally used as standard? Is it code specific fields, or is it just useful?
Good question. I don't know if I can have enough to answer that. I know that, well, you're a math major, and I never have seen it done this way in math books, if that's what you're getting at. I've only seen it done in science and engineering books. So, anyways, but as long as we agree on what we mean by this is what I mean. And eventually I'm going to take an integral, and this is a variable. So maybe I'll just move that to the outside here right away, and so that there's no confusion. This is an R, this is an I, this is a B, this is a dr. Right? And so everything in here could change. So when I go to calculate the total torque needs to be added up piece by piece by piece by piece by piece. So I need to start at the inner piece of the toroid and go out to the outer piece of the toroid for my R, my I, and the magnetic field is N mu naught I over 2 pi R dr. And so there's the beauty of this device, in the sense that the field gets weaker 1 over R, inversely proportional to R, but the torque increases in proportional to R, then they cancel off. And so you get, and maybe I should be careful here, because this is the current in the toroid, so I'll put a T, but this is the current in the lever there, so I'll put the catenary there. And so what I end up with is current in the cantilever the number of turns, mu naught, the current in the toroid, the 2 pi, and then this, the 0.06 minus the 0.05 for the distance it does. And then all of that comes into an enormously large current of 194 amps. And seems like a lot of current in order to lift up a lousy 50 grams. And it is, and that's actually why I put that little comment there. In case you got that number, you wouldn't want to sit there and go, I must be doing something wrong here. Because as I then kind of look at you guys and say, did that make sense? Any questions? Because there were two things that we didn't quite get to in chapter 30, and which is fine, by the way. But those two things are the magnetism of material like iron. And as I think I mentioned, I'm going to use the start of this next chapter as a springboard into that. And so I thought I would start then our next unit by using this problem number 5 and show you some electromechanical devices here. Probably the simplest place to start, and I already showed you that one, but I want to do it again, is just to come back here and say, all right, look, if I take a solenoid and I hook it to my power supply, here is 180 turns of my solenoid. And if I turn the current on, and actually let me get a little longer wire so I can have some more workable room here. But if I take my solenoid and I turn this thing up to full current, that should make a magnetic field, right? That should be able to pick up a nail. Oh, yay! Yay! And so there was the idea, although I can't pick up a box full of them, maybe a little bit. Let me turn it off, it's starting to get real hot. But, you know, I'm putting like 15 to 20 amps through this thing, and I'm picking up like 1 or 2 nails. Really not something to brag about, okay? But it's working, right? What if I were to put a piece of iron in its core? Any difference? And I'll give this a chance to cool down here, but this is what that picture is. This is that last section in 30. It says, what if you added iron to something, or any material, and then there's different effects from different material. But let me pick on iron, because I just want to give you a demonstration and then say, all right, the magnetic effects can really be amplified with the material. Why? And I just want to leave you with a conceptual picture and say, calculations will follow next year. And so this is our magnetism. This is our first step with just, hey, where does the magnetism come from? But here's what I want you to see. I want you to see in this picture that if, ooh, still hot. If I take this, there will be a magnetic field along the axis of the solenoid. But then I take some material. And the reason that's important is, aren't there many, many electrons here? And even though I have, 15 to 20 amps of current flowing in this guy, that number of electrons moving is very small to all those electrons that are in this atom. But they don't pick up any nails. Why not? they're not what I would call synchronized, if you will, right? They're not all going in the same direction. If I was drawing a picture of this, I guess it would look something like this. Here is my piece of iron, and I would have some electrons that are going clockwise, some that are going counterclockwise, and of course that's just a simple picture of a more complicated three-dimensional picture. So some are going in this plane, some are going in this plane, some are in this plane, some go clockwise and counterclockwise. But by the time I take billions and billions and billions and billions and billions of them, equal numbers clockwise and counterclockwise in every single plane, what's the total magnetic effect? Zero. But what if I can get them all to orbit in the same direction, in the same plane? Wouldn't this be the equivalent of not just 20 amps, but maybe 20,000 amps? And it's very easy to make this equivalent to 20,000 amps if I get them all going in the same direction. So this alone can make this 1,000 times stronger. Actually, our cheap iron is only 500 times stronger. All right, so I'm going to make it whatever, only equivalent of 10,000 amps. But you'll see it right here. And here's the trick. I will use this small field to make these align. When these align, these will make a very strong field, and I should be able to pick those up. And that's what this picture is trying to show here. They're trying to show that this is the atom, this is an electron orbiting. They go one step further. They say, don't forget that not only is the electron orbiting around the atom, it is also spinning like a top as it orbits around. And so we can get a magnetic effect from both of its orbit and its spin. And if I can get them all to line up, and I probably should be careful there because I'm just trying to give you a conceptual, I won't even get close to all of them. I'll probably even get not even close to 1% of them to line up. But 1% of them will still be 500 times stronger than the amount of electrons I have in that wire.
So is there limits to how many times you can amplify this process?
Well, the limit is how many are you going to get to line up?
Couldn't you use the magnetic field that creates to make another bigger piece align, and then that would create a bigger magnetic field and bigger person?
To a limit, because again, remember, this thing needs to hold together, and to hold together, the structure and the pieces of the electrons and the solids need to be aligned and be very strong. So if I were to actually get them all to line up, then they wouldn't have the bonding between them, and this whole thing would just fall apart into a bunch of little pieces. And it'll actually end up exploding. How's that? And so there is your magnetic field. Sunspots are a good example of that. Solar flares are good examples of that. The magnetic field will build up, build up, build up. And then as these things all get aligned, they get weaker in there, and then they just release all their magnetically stored energy into a kinetic energy. And so we get these. Well, anyways, what I want you to see then is with the core in here, you will be able to hopefully see that it is many times stronger. And by turning the current on and off, I now have the ability to control things in terms of what I'm doing is using the current here to make what you might call a small field. Then that small field makes the big field, and so the cores can make things many times stronger. And so this whole number we calculated at 194 amps, really we could do this same thing at just a fraction of an amp, probably a milliamp.
Why doesn't that become a permanent magnet?
Oh, well, and then the other thing here is that this is what we call soft iron. And the atoms can actually turn a little bit. And I want it so that they can turn in the direction to make the field. Now, why don't they stay there? You'll notice I turned it off. Well, they have temperature with them. So don't forget, on a microscopic scale, these atoms are hitting each other. Okay? So they're going to line up only because the magnetic field here is helping them line up. They're going to disalign because, remember, they have temperature. So if this was at a lower temperature, and I don't know what it would take, but let's say at 100 Kelvin, it would probably stay a permanent magnet. The other thing is if it was already under 100 Kelvin, that means the atoms are locked in, and getting them to twist probably won't happen. So I got to put them in the magnetic field at the higher temperature, then cool it down to the lower temperature, and then they'll stay locked. Is that what you mean?
Yeah.
And every magnet is like that. This, though, just happens to be at a lower temperature. It's why it's a soft iron. It's not very strong. Not that I can bend it, but you wouldn't want to build a building out of this. It's very weak because the bonds between the atoms aren't that strong. Whereas what you saw me work with before, here, these bonds are much stronger and they stay aligned. And so this was made by first heating it up really hot and then aligning them and then cooling them down here. And so this will stay. Actually, this is kind of in between. This is not. I mean, this one I could sit here for a couple hours and bang on it, and this would not be magnetized anymore once the atoms stop. But the nice thing about this iron and the soft iron here is now I can turn off the magnetic field. So I can turn it on and pick up the pieces of metal, or turn off this one, the controlling field. And so that's the concept I wanted to leave with. So I thought I would start our next unit, which, as I said, is really kind of the end of this chapter, and say, you know what, I should show you some of these electromechanical devices so that you'll understand the workings behind them. And so I have this one here, just to emphasize the strength here. But here is one that has only 2 batteries. I mean, this is 3 volts right here. I suppose I should have checked if these were new or not. Well, we'll find out. But if I turn this on, there is current, and you can't see the wires, but there's the core part that I wanted to emphasize. So if I take this end of the metal piece and I hook them together, right? Nothing's sticking yet. If I align it and turn it on, it should, oh yeah, stick. And with incredible amounts of strength. Hopefully, last time I hit myself in the head. So, okay. So it's designed that I can't pull it apart, yet I can easily just turn it off and take it apart. So it makes a nice electromechanical device here that I can hold something or not hold something. And I'm only looking at 2 small batteries.
So as far as the energy, when you had the piece of iron in the solenoid,
Yeah.
did it use more energy from the power supply when we were picking up the nails as opposed to not picking up the nails? I mean, when you added the iron,
Yeah.
did it use more energy than before we added the iron?
Oh, I'll say yes for now until we get to the rest of this chapter. How's that? Yeah, yeah. Because there's a small, and you're doing in your circuits now, an induction effect, which is the start of this chapter and the next chapter.
So the only extra work that was being done is while the nail was moving through the magnet, and then it was no longer doing any extra work.
Right. And then, so if I guess if I had it over here, okay, I'd have a strong magnetic field. When I put it near here, that field gets rearranged, if you will, and that's then where the energy went. Now the energy I think of lifting it, though, is what part I don't want you to confuse. That's me, right? Except for this part. Ooh, it's getting hot. If I were to have it on here, here's where the energy comes from the field. I mean, this could actually lift it.
While the nail's moving.
And so while the nail goes up there, the nail itself, the iron in the nail, affected the field. So the energy was stored in the field. Now we have a reduced field, kind of like the dielectric was when we put it in the capacitor. We had a reduced field. Where did that energy go? Well, that energy went to the store, which in this case is gravitationally lifting the nail up. And so we've got a transfer, if you will, from magnetic energy into gravitational potential energy. And if we pull that nail back out, we got to put work into it to pull the nail out, and thereby adding energy back into the magnetic field. And so, we still have our conservation of energy. Well, again, at the risk of maybe taking too long on this, because I'm not going to really have you read about it, do any homework on it, or even test you on it. So keep that in mind here
So
on
the
this
second part
this
of
one.
the chapter 30 homework is never going to be due.
Hang on with just that. Section 6. Section 6. Section 6. But section 5, yes. If that makes any sense. Okay. Just because we're low on time here. But I thought, like I said, I thought I would want to show you that, because here then makes a fun device. This is a relay. I grabbed this one. I'm just going to pass it around here. As you can hopefully see then, if I plugged in, and there's a bunch of connections here, but if I were to plug in right here, the current would flow here, turn this magnet on, which pulls this down. And so I want to pass this around, and I want you to just kind of tap on it and realize that if current flows in here, it'll flow into this coil right there. It'll pull this down, and this makes contact up here. So we have our electromechanical. And in this case, it's a switch, because then we can make contact and turn things on and off. So as you're playing with that, I'll actually use one for you. Here is a good example of this switch. I have here a light bulb. Now, I'm sure you're familiar with the whole idea that a light bulb that is at least plugged into your house here is plugged into 120 volts. A little high in voltage, a little dangerous if you're not careful. So what I'm going to do is to plug it in. Except, you'll notice it doesn't go on. Why not? Because the switch that turns it on, which, you know, on a wall you would just move the switch up and down, is a little relay right here. It's one of those. This will not turn, or this will turn on the switch when there is current being applied to it. And it is nothing more than a solenoid with a metal core. So it won't take much current. It won't take much voltage. And so here's the idea. If I take this same power supply and turn the voltage down to, say, 6 volts, so I'm going to set it at 6 volts and plug it right in here, right here. Here's what I wanted you to see, and it looks like it was already crossed there and spooked me, but there is the 6 volts traveling to the relay. Hence, touch it, taste it, cross it. But it's not controlling the high power, fair enough? And so I'm using an electromechanical device, a very safe low 6 volts, to control, and it's in a little plastic insulator, the 120 volts here. And so there is my control power. I mean, how do you turn the power back on to a power grid that is supplying 10 million watts to a city? A switch? Do you really want to be the person putting the two metal wires together? This is not how you make the connection for something that is high power, or things that you want to be able to turn on and off with just a simple small circuitry here. So again, small here, controlling big there. A good example of that is starting your car. You may not recognize this, but this is part of the starter motor of your car. This is your solenoid. If I put current into this solenoid, it will make an electromagnet. It will pull that in. And so there's our electromechanical device. In this case, there would be a pinion gear here, and then this would engage, and that's how the starter motor would engage with the flywheel on your car, and your engine would turn over. But in order for me to send current through my starter motor, okay, or for that matter, even send current through this one, but my starter motor is hundreds of amps. Do you really want to be sitting in your car seat with your key, turning it to the on position, with hundreds of amps coming through the steering column and going back out? I mean, just a recipe for fire to start in there, right? So that's not what actually happens. What actually happens is when you turn your key to the start position, you are making a connection to a relay. The relay then closes in the engine compartment, making the current go to the starter motor. And not only the starter motor, but also this solenoid, which then engages. And I think you can see that if I take a couple of these wires here and say, all right, this is going to need a lot of current. So I will put the plus to a switch. So here's my tap switch. From here to my electromechanical device. So I'll clamp right there. And then I'll finish with another clamp on my electromechanical device. Oh, I hope that'll stay on. Probably not. Well, at least it'll do it one time, because this thing will probably shake the whole table. And then put it here. Keep those separate. Thing look good? Nothing crossed? Maybe I better hold this down a little bit. But when I put current through here, there's going to be a lot of amps that go through here, and it pulls this in. And it can be significant in its movement. Ooh, got me. But you're probably more used to it. Something maybe not this strong. But isn't that what you do when you hit the remote and you see the locks go up? Locks go down. Why do they go up and down? Because underneath that door is a nice little cylinder. And you're just doing that, and then the current goes in and out here. So one more, and then we better jump into what is section 5, because we need 5 before we can go to the next chapter here. But here's one of my favorite ones. Look carefully at this one. This one has a wire, which eventually I'll hook to the plus there. But this wire comes in, and it goes up to a little metal piece here. Then there is a second metal piece called points that then come down. It's actually spring loaded, if you will, because this wire then goes through a solenoid. All right? Maybe that's not a very good picture, but does that kind of make sense? I mean, what do you think will happen now when I hook this up to a power supply? Plus minus. Current's going to go through, and let's say this spring is pushing enough, so this is a spring, that these close, which is what we have here. We have them in their closed position. Isn't that going to make current flow through here? And when current flows through here, what will this become? A magnet. This happens to be made out of iron. So when this becomes a magnet, what do you think it'll do right here to where these contacts are? Pull it down. And once it pulls it down, what happens? Yeah, it pulls it down, right? Doesn't that disconnect the current? So if there's no more current here, is that any longer a magnet? So what happens? Spring pushes it back up and makes contact. Then what happens? Right, and then this just continues, right? This pulls down, goes back, pulls down, goes back, goes down, go back. If at the same time, on the end of this piece of metal, you put a little hammer, surrounded by a piece of metal called a bell, you will see pushes down and the little hammer hits the bell. And so it pulls down, rings the bell, then resets, and then hits the bell, and hits the bell, and hits the bell, and hits the bell. So, if done right, we should get kind of this on-off effect. It goes on, it becomes a magnet, pulls it down, stops it from being a magnet. And so, let's see if I can, well, actually, I'll just disconnect this whole thing. I think these wires are long enough that they can reach my bell on its own. So if I put one here and one here, okay, I'll get, again, another electromechanical device here, a kind of on-off using the magnetic field. All right, yeah. Shouldn't have rang the bell. You're going to think class is over, right? All right, well, here's what I wanted to say, and I jumped right into it right after going over the test, is that there are two sections still, three really, in Chapter 30 that we didn't quite get to. We did sections 1 through 4. Section 5 has to do with magnetic flux, and that's where I want to begin. That's an important one. We need to go back to our magnetic flux. Fortunately, it's very easy as we get started into the next chapter. The section 6 and the section 7, I'm just going to say, let's just bypass those. Section 6 is what I was just talking about, that the magnetic field can be increased or decreased, but because of the material itself and because of the electrons that are orbiting there. You'll do more on that future, and this I just wanted to set up you conceptually. 7 is the Earth's magnetic field, and I think we actually covered that pretty good in an earlier chapter, but if not, I'm just going to say, we need to move forward here. We're a little bit behind here. So all that is to say is, let's just, as far as test material and as far as homework material, only worry about sections 1 through 5. We've already done the test on sections 1 through 4, and section 5 has the title Magnetic Flux, and that's where I want to spend about 3 or 4 minutes, maybe 10 minutes, saying what is magnetic flux. Yeah, so this is chapter 30, section 5. Okay, so I would encourage the following, that you look closely at this. Turn in 30. Some of you already turned in 30 without doing section 5, and that's fine. Not going to penalize you in any way. But before the test, you'll want to go back and look at those problems so you can do some calculations with flux. I meant to have some time to look up what number those were here. But I'm not really even worried about the homework or the chapter for the rest of this part. We just need to know how to do flux and talk about flux in order to do the next chapter. So I really just want to focus on the next chapter. That's my point. It's chapter 31. But I feel like before you can get into 31, I got to say a little bit about magnetic flux. And for that matter, I'll mention it in passing, but as you'll see, Gauss's law of magnetism is also in here. And it has to do with flux, and it's really not very helpful. So, true nonetheless, but it's not like Gauss's law of electricity, where we use Gauss's law again and again and again. You'll notice we used Ampere's law again and again and again to get the magnetic field, not Gauss's law of magnetism. So I thought I better start off by saying, what is magnetic flux? Well, maybe I should come over here and say, what was electrical flux? Anybody remember? I know it's been a while. All right, so it was the sum of all the little lines that went through a surface, right? The little lines, the electric field, were represented by E. There was a dot product, there was an area, and we had to sum it all up, right? We use the little symbol capital Phi sub E for electrical flux. So I want to get started by, what do you think we're going to use for the symbol for magnetic flux? The capital Phi with a sub B for magnetic flux. And if I give you really the same picture that you saw in chapter I just smell something warm. Okay. See if I left anything on. Maybe it's the computer over here. Yeah, I think it's the computer. All right. But if I come back over to one of these pictures, here's where your author gets started. And you can see it's almost in a direct duplication of what we saw in chapter 24, where what we did is we took a little surface, this is a brown surface if you will, and we said let's look at a little area perpendicular, let's look at a magnetic field, and so the total flux would be the sum, that is the B field dotted with dA, then added up over the whole surface would be the magnetic flux. And so that's why I said I don't think we're going to spend much time here. I just want you to remember what flux is. We haven't used magnetic flux, although I have noticed a few times even today before in the last hour, I said the word magnetic flux, and I don't think the book has used the word magnetic flux. We used electrical flux a lot, but not magnetic flux. But I think you get the idea right away here, is that it is a combination of the strength of the magnetic field, the area, and the angle. Oh, for example, in A, how much electrical flux do we have going through that brown surface? 0, right? It's not that we don't have a surface, right? And it's not that we don't have a magnetic field, but what happened here is because the surface is laying flat, nothing is penetrating through the surface. How would you align it to get the most flux through that surface? Well, that's what B is trying to show here, right? Where you would have the dA and the B in the same direction. And so, taking a piece of paper like this, we can, maybe a calculator might be better here, but taking this as my rectangle, I can look at this and say, how much flux? And it would be like, how much of a shadow do I have? How many light waves do I block? And if I hold it up here, and if I twist it sideways, or depending on the angle, I can get a different shape to my shadow, a different area. How much flux is there? And so that's what flux is. Just how much do you have in terms of the magnetic field and the area? I say that because let's just try a quick calculation before we leave the chapter here. Does this make sense? Could I calculate the flux that goes through a rectangle that has a width of A and a height of B? It happens to be a distance C away from a wire that has a current of I. Could I get the magnetic flux through there? Oh, let's just start with a mental picture. Magnetic flux would mean there has to be a magnetic field. Where's the magnetic field coming from? The wire itself, right? And so we can have wires or solenoids or toroids. They can all supply the magnetic field. And they are. And in this case, we've got the simple wire, so I'm going to take my right hand, I'm going to grab it with my thumb in the direction. You can see that on this side of the wire, flux would be coming out. They don't even label it. It would arc around and go in right here. And so they've given a bunch of X's in green to show this is the magnetic field. So the magnetic field on the right-hand side of this wire is going in. Okay? And that's what they want you to see. And the flux then would be how many of these are going in this rectangle? Well, let's start with the dot product. The first idea is B dA cosine of, what would the angle be? It's 0, isn't it? Now let's start with the direction. I just told you that the magnetic field is into the board. Where's dA? Well, dA is perpendicular to the surface. So if here's a rectangle, right? We hold it up here. perpendicular to the surface would be, I'll use the pen, would be in. Or I suppose you could argue out, but let's just find the magnitude and we won't debate whether it's 0 or 180 degrees. You'll see why in just a second, but we'll just call it in. And so there is an angle of 0 degrees. So the first step reduces down to that. Next step. Well, what is the magnetic field from a wire? Well, net mu naught I over 2 pi r. Right? And what was r again? Distance from the wire. Okay. Now, here's what makes the problem a little hard mathematically is the field changes, doesn't it? The field is stronger as you get close to the wire here. And your author has it labeled this way. He's got the x's a little closer together here than here to illustrate. Look, here's where the field is strong. Here's where the field is a little weaker. And so it goes stronger and medium and then weak out to there. Okay? And so obviously the amount of flux that goes through this little part of the rectangle is different than that part. But I've got to add them all together. So then I have to add up the whole rectangle. And we might as well do it in strips. And you can see the author has given you this tan strip down the middle and says, look, one thing nice about this tan strip is it is all the same distance r away. And so the strength of the magnetic field within that strip is the same. Now, each little strip would have a different strength to the field. But the field within that strip would be the same. So I would replace my dA with the area of a strip. And I'm going to add up strip plus strip plus strip plus strip. And so that would be the, what is that dimension? B times a dr. And so your author's trying to say, look, this is how you would calculate the flux. You would have a B and you'd have a dr. And now go ahead and add it up. What are your limits? Well, we're starting at a distance of c. So the first strip would be right here. We're going to add it up till we get to the last strip, which would be a plus c. And so a plus c. All right. So again, not anything new except for the fact that we're using the word magnetic flux instead of electrical flux. Also, it's been a while, so I go, you know, I'm going to take a few moments here and do a calculation for flux. And so there is my calculation for flux. Things that are a constant like mu naught and I can pull out. The 2 pi I can pull out. The b I can pull out. And then I just have an integral of 1 over r. What's the integral of 1 over r? Yeah, ln of r from c to a plus c. And so the amount of flux is mu naught IB over 2 pi natural log then of a plus c over c. And so there would be my calculation for the amount of flux. So again, just like we did in chapter 24, we said electrical flux. Of course, now we need to make the next step. Why do I care about calculating the flux? What usefulness is it? Yeah.
Why do they have R starting at the center of the wire, but C starts at the edge of the wire?
I do not know.
C starts at the center of the wire.
I don't think they are saying, I think they're just doing a poor job of saying it's the center.
Okay.
Yeah. I don't think they're trying to, without giving something about the radius of the wire, they're not trying to point that out. I mean, so. Well, like I said, does this kind of make sense? Because there's flux. Now, last time when we did flux, we did Gauss's law. So let's look at some flux. Maybe this is the magnetic field from a a bar magnet, or maybe it's a solenoid. Don't really know here, but we learned something. That there was no such thing as a monopole. What does that mean? Yeah, there's no place for the electrical flux to begin or end on, right? This is not like electrical charges. Right, let's go back to electrical charges here. Your author compares and contrasts this. He says, look, here is north-south, here is electrical flux. Okay? And so again, if we go all the way back to chapter 24, he says, look, when we did electrical flux, and we drew a closed surface, we realized that if there were not any charges inside of that closed surface, you would have the same number of flux lines that go in and go out. Fair enough? And so what we ended up with over here was that if you then took the electrical flux in a closed surface, it would equal to the charge inside divided by epsilon naught. Remember that from Gauss's law? But if you don't have any monopoles, what would happen over here then when you say, let's look at the magnetic flux when you have a closed surface? What's going to happen? Yeah, you're always going to get zero. And so just like we had Gauss's law for electricity, which was a very powerful statement because it allowed us to find the electric field, if you remember all that time we spent on it, we also have what we'll call Gauss's law for magnetism. Unfortunately, it always comes out to be zero, whether the field is big, whether the field is small. Not to say it doesn't have its usefulness, but it is a statement of saying there is just no such thing as monopoles. And it really doesn't help us find the field. So if you recall, we did not find the magnetic field from a toroid using this. We used Ampere's law. We did not use the magnetic field from a solenoid or a wire. We didn't use Gauss's law of magnetism. So I feel like I should at least point it out because it's there in the book. What we're going to want is flux, definitely, but not necessarily a closed surface. And that's what I really want to point out. If you have a closed surface, it always comes out to be zero. Your author shows you a couple pictures of it. Like I said, he went back to electric fields to remind you that for electric fields, it doesn't always come out to be zero. But magnetic fields, pick anywhere you want on here. Pick any place that's closed. You could go here, you could go here, you could go here, you could go here. But since there is no beginning and no end to the magnetic flux, there is no equivalent usefulness like Gauss's law for electricity. So, not usually useful in the sense of finding the magnetic field. What will be more useful is what we're about to do next, where we will talk about flux, not on a closed surface, but just a nice flat rectangle. This will be a very powerful calculation for what we're about to see next. So, with all that said, I will then start chapter, what is this, 31. 31, you might be happy to hear, is one of the shortest chapters, if not the shortest one in the book. Visually, conceptually, ooh, tough. And so I think that between those two, hopefully they balance. Short, but tough. Watch. Here is Faraday's law. Faraday's law says, let's look at the flux. And we can look at different scenarios of flux. I think I'll start by just writing out his description. Maybe the first picture I'll put up here is, okay, here is a rectangular loop, and we have some magnetic flux that goes through it. That magnetic flux could have simply been created by a bar magnet, and so I could do something like this. Here's a bar magnet. I will put it near this loop. Maybe I'll move it back a little bit. Maybe I'll move this magnet out of the way for now. And say, okay, here is my, actually, you know what maybe it'd be better if if I didn't do anything yet. Let me build up to this. Okay, I'm going to start here. But here's a loop, here's a bar magnet, right? That bar magnet is sitting close to that loop. Would you agree then that there's some flux going through there? Faraday noticed this. And this is the whole chapter in a nutshell. Faraday's law. Faraday's law of induction, to be more specific. It says the magnitude of the induced EMF in a circuit equals the time rate of change of the magnetic flux through the circuit. Now there's a lot in that little statement. This is going to consume a whole chapter here. But the biggest one is to realize, wait a minute, what is EMF again? I haven't seen that for a while. Electromotive force, what was that? Do you remember doing that? Remember doing that for batteries? I mean, maybe a good review here is worth putting on the picture. I mean, didn't we do electromagnetic force? I mean, how does this have to do with magnetism? I thought this was electricity. I mean, didn't we do problems like this? We said, okay, let's take, say, a battery, and what we said is there's an EMF inside with an internal resistor, something like this, right? And then we said, well, what happens if you put that with a load resistor? Right? I mean, wasn't the EMF the voltage? I mean, didn't the voltage come from the chemicals inside, right? Didn't that voltage come from an electric field? What is this first sentence saying? It is saying the magnitude of the induced EMF. Wait a minute. What you are telling me is there is a second way of making an electric field. And that's probably the most important thing I can say here at the beginning. Did you catch that? Because we have now crossed a very interesting line here. We spent weeks talking about electric fields. Fair enough? Electricity. Now we've spent a little bit of time about magnetism. And now we're ready to go to electromagnetism. The two together. Before this semester's done, here's what I hope you'll get out of it. Is right now we have learned, how do you create an electric field? Charges. How do we create magnetic fields? Moving charges. In the next couple of weeks, we will hopefully learn that there are two ways to make each. You're learning the first one. How do we create an electric field? There are two ways. The first one we spent weeks already studying. Charges, batteries, chemicals. Did a lot of that. Okay, they all have to do with the charges. What is the second way? Did you catch this? The EMF is equal to what? The change in the magnetic flux or the magnetic field. And the point I want you to get here in these few minutes that we have left is that there is a second way of making an electric field. It's far more interesting, far more complicated, far more useful. Okay? Is that you can create an electric field with charges, But you can also create an electric field by changing magnetic fields. Moving magnets make electricity, if you can remember that phrase. Okay? Watch. I have over here, as simple as it is, an ammeter. It's a big classroom one, so you can see it. I have it hooked up from here to here, back to here. And if I can do nothing more in the rest of the time today is just convince you that there is a second way of making electric fields. It has to do with changing magnetic fields. I say that because don't I have a magnet right there? Am I getting any current? Is it magnetic fields that create current? No. What creates the EMF? What creates the current here? There's got to be a change. So how can I get a change here? What if I take it away? Did I get any current? What if I put it in? Take it away. Put it in. Take it away. Put it in, leave it there. Does this create any current? No. Why not? All right, so what I want you to see in these little demos here is there is an EMF. The EMF is produced how? Changing magnetic flux. It's not just a magnetic field creates an electric field. You following that? You have to have a change. Could you put these words into an equation? EMF, right? EMF equals what? Okay, it equals voltage. But what is the rest of that statement saying?
Changing magnetic flux of
All right. So how do I put those?
derivative of magnetic flux.
Isn't that what it's saying? Is that how you read those words? All right. And so my goal here today, and then also followed up on Thursday, is to show you this calculus. Look at the calculus. It's got vectors, it's got dot products, it's got an integral over space, it's got a derivative with respect to time. A lot of math there. Okay? But before we get to the math, look at this whole idea. It is saying that there is an EMF. There is a second way of creating an electric field. So, watch what happens. If I pull this out, I get a current. I push it in, I get a current. As long as there is change. Now, here I'm moving the magnet. Could I move the coil? Right? So it doesn't matter which one moves as long as one is moving. There is an EMF. In fact, it gets a little bit better if I, where'd that big one go? Connect it probably a little bit closer to where we're headed here in a second, and where you're probably very useful or familiar with the world around you. When you plug something in right here, we've been saying for a while that this is an AC current. What do we mean by that? Alternating current. Why? It changes. It goes left, right, or clockwise, counterclockwise. Why? Here's a magnet. What happens when I spin the magnet? Do I create any current in here? I don't I, right? Because what happens is this guy here has some flux. And if it is then rotating, and so this is spinning, maybe because water is flowing through it, or maybe the wind is blowing on it and turning it around. But as this thing spins, the flux that goes through here keeps changing. And it would go clockwise, counterclockwise. The flux would go in, the flux would come out, the flux would go in, the flux would come out. If you stop spinning, do you create an electric field? Right? So the second way of creating an electric field is we have to have a changing magnetic field. We have to have a change in our flux. And that's Faraday's law. And that's what everything up here is really designed to illustrate. I'll pass out two of them here to begin with. Here's a very simple one. It actually matches the one that you've already used in lab. This one in the lab, I just brought it out to remind you. It doesn't make a good demonstration one because you can't see the moving parts. But you might remember that you took it out and you were spinning. What was going on here, you think? Yeah, you can hear the gears moving around, and they are moving a magnet. I'll leave this one up here because I like this one better. You can actually see, there's the magnet, there's the gears. Squeeze. Magnet spins. Light. Right? Moving magnets make electricity. And so as long as I have a moving flux, and in this case it's just spinning in a circle, through the coils that are here, it will produce current. The current runs through a light bulb. And I see the light. Second one. Not exactly ergonomically as nice, but scientifically fun to watch here. Here is my flashlight. If you look closely at it, you will see there is a magnet. There is a coil. If I turn it over, the magnet will fall through, and every time it falls through, it produces current. Because an EMF is produced by changing magnetic flux. So, if I were to do this, can you see the light go on and off? If I were to turn it off and do this for a couple minutes, I'm charging up a capacitor. And so, just like this one, if I spin it for a couple minutes, I charge up a capacitor, I will get a light that stays on for a few minutes, depending on how much charge I built up on that capacitor. But again, play with it as you will. Let me show you some others here. But the whole idea here is moving magnets do create some electricity. Ah, here's a fun one. Anybody recognize this? Comes out of your car. It's an alternator. Generates electricity for your car. How do you think it works? There is a belt that comes around and spins this. What's inside, you ask? Not a surprise. Magnets. Coils. Moving magnets make electricity, right? And so there's our changing flux here as we design how it's working. Oh, how about this one? Here's where I think it can get even a little more interesting here. I'm going to take this power supply. Maybe I'll put it close by. I'll go ahead and put what we've been working with before. Here's my coil. Here is my coil with a core inside. I'll put it in here. I'll take a couple of wires. And I'll put my wires here. Actually, maybe I'll just move this over to here. Any electricity generated? Any suggestions how I might make that meter move? What do you think might happen if I turn this on? Maybe I'll get on the other side so I don't block your view. But if I were to stand over here and turn this on, did you see it move? Is it generating any electricity now? But this is on. What do you have to have? A change. And I can't overemphasize that. It does not just say you are going to get an EMF for any reason, for any magnetic field. What do you have to have? A change. So if you'll notice, what happens when I turn it off? Turn it on. Turn it off. Right? And so I only get a change as the current is increasing or decreasing in this coil. So as long as it's fully on or fully off, that is not inducing a change in there. And so again, can't overemphasize. But it is not just flux, it is change in flux. We have to have the flux change. Watch this one. Here's a fun one to do. This one is plugged into the wall. And so, I don't know if you can see the power cord, but it's plugged into the wall. What did I just say a few moments ago about the current that comes from the wall? Alternating. It would be like somebody standing over here turning this on, off, on, off, on, off. Fair enough? So, what do you think might happen if I come over here and I turn this on and I send this current to this big coil? Isn't it going on, off, on, off, on, off? Maybe I'll start with this one. What happens if I put, uh-oh, not getting much power. Can you guys even see the light going? Yeah, barely. Let me see if I can get the core a little closer to the top. Maybe that's it, but I think I got some resistance here in my wires. Am I plugged in? Plugged in. But what I do want you to see, maybe that's a little better. Well, maybe I'll play with it. But can you see it go on? Can you see it not on? How come it works here? Where's the changing field? All right, and then some of these get a little more complicated. As you can see, when I had the magnet and I was actually moving it back and forth, you could actually see a movement. Do you see any movement here? No, but is there a change in flux? Yeah, and where's the change in flux coming from? The fact that the current changes in here. And so watch this. What if I switch it to here? Turn it down a little bit. Turn it off. Turn it on. Why? Why does that hover like that? Yeah, we got to put a lot together here. I'll start with what I'm trying to show you now. This is Faraday's law. Isn't there current in here? And the current is constantly changing. And the current is going to change, and as the current changes, what is it going to do into this ring? Yeah, it's going to make a little EMF. And that EMF is going to make current. And now once there's current in here, what's happening here? This too becomes a magnet. And this magnet and this magnet repel each other. And so I need to put together this chapter together with the last chapter. It creates an EMF. The EMF creates a current. The current makes this one a magnet. These two magnets end up repelling each other. And in fact, you can see it well with the difference between this ring is that, and I don't know if you can you see from that end, we've cut the ring with the bandsaw, so it's not a closed circuit. And so if I put that over there, I'll get some flux through here, which will make a voltage, but will I get any current? No. And if I don't get any current, then this won't become a magnet. Fair enough? And so, this one and this one have very different effects. Even though Faraday's law is saying you'll produce a voltage, this produces a voltage but no current. This one produces a voltage or an EMF with some current. The current makes a field. The field opposes the other one. Well, shall I show you one more? Nah. One more? No? All right, well, I'll stop there. But I got where I wanted to go, and I wanted you to see it conceptually, because now we got some tough math to do, some real tough math to do. But fortunately, short chapter. One equation, that's it. How hard could it be? One simple equation, right? All right, one hard equation, but only one.